The necessary adhesive properties of building mortars and where these come from. This is an extended version of a presentation given on the 8th of December to the York Consortium for Conservation and Craftsmanship. What were the historic understandings of what a mortar was for? Mortar ought to serve at least three purposes. It ought to form a soft but gradually hardening bed to receive the various building materials, so that these shall obtain a uniform bearing notwithstanding the irregularity of their surfaces. In the second place, it ought to prevent the passage of wind and rain through the joint of the walling, and lastly, it ought to have adhesive and cohesive strength enough to bind the component parts of the wall into one solid mass. It is frequently said that mortar was simply to hold the building units apart. Now, that's true in a sense, to provide a deformable cushion between these elements, but primarily, and of equal importance, I should say, they need to bind those materials together in a consistent bond. Mortar strength is often greatly overemphasized to the detriment of other essential mortar properties, such as workability, water retentivity, and bond strength. And those builders who strive for high or maximum mortar strengths usually obtain inferior mortar for normal above-grade masonry construction. We might add that a mortar ought to possess appropriate functional performance, offering efficient capillarity in the drying of traditional fabric and the keeping of it dry, as well as offering potential sacrificial behavior and a generally compatible compressive strength. Modern NHL mortars generally don't offer these things. These understandings remain in the modern ASTMS guidance for mortars. Workability is the most important property of a plastic mortar. Workable mortars can be spread easily with the trowel into the separations and crevices of a masonry unit, into all of those, not gliding over them. A workable mortar also supports the weight of masonry units when placed and facilitates alignment. It adheres to vertical masonry surfaces and readily extrudes from the mortar joints when the mason applies pressure to bring the unit into alignment, but importantly without squashing completely, resisting that press, as well as giving. Workability is a combination of several properties, including plasticity, consistency, cohesion, and adhesion, which have defied exact laboratory measurement. The mason can best assess workability by observing the response of the mortar to the trowel. Good workability is essential for maximum bond with masonry units. By maximum bond, we mean adequate bond, not really strong bond, but an adequate and appropriate bond. Workability was the standard historically, not as a nice to have, but for all the important mortar properties and behaviours that it indicated. If we look at the ubiquity of hot mixed lime mortars historically, this is an analysis of the 4,000 samples from the database of the Scottish Lime Centre Trust. The blue in this picture is hot mixed lime mortar, and in most cases, the vast majority of cases, non-hydraulic or feebly hydraulic hot mixed lime mortar. The red, bizarrely, one might think, given the history of the lime revival, the red is lime putty, and even that, were these mortars hot mixed with powder, might be red. They might be red as lime putty, being used as a binder. Some earth lime mortars, coupled with pure or very nearly pure lime finish coats from Moulton and the North Yorkshire area. Got earth lime plasters with pure lime plus 10% limestone aggregate in the top left. Hot mix finishes over earth lime base coats to the right, and still well bonded earth lime bedding mortars to a calcareous sandstone. An analysis of an earth lime plaster from within York House was mixed with one quicklime to 3 clay-bearing subsoil. And note how very fine the dominant aggregate particle size within this is. We've got clays, very fine. We've got silts, very fine. And the silts really are as important to the performance of these materials as is the clay, and as of course is the lime, which stabilizes this material and reduces expansion and contraction during wetting cycles, amongst other things, and transforms an earth mortar into a beautifully workable, cohesive, adhesive material, entirely similar in its feel and behavior to a hot mixed lime sand mortar. The ordinary or common method of hot mixing with lump quicklime here in Canada, quick, efficient delivery of eminently workable lime-rich mortars, alternatively, of course, made in roller pan mixers. Here in Thornton-le Dale, where I'm talking to you from now, a 400-year-old haired Airline mortar over earth-built limestone fabric, 2 parts lime, 1 part limestone dust, hot mixed and used a while after cooling. An attempt to imitate or to reproduce a very similar mortar as common, this one without any addition of limestone. So local non-hydraulic oolitic limestone burned in a small scale kiln, slaked to a dry hydrate fresh from the kiln, mixed immediately while still hot, of course, to a mortar, hair added and pointed into a minimally pre-wetted wall while still hot. Barely any shrinkage initially, leather hard 12 hours later, and dressed back, and the face carbonated after 4 days. And just, we need to mention the elephant in the room, in the lime room, cement lime mortars. There are buildings all across North America. There are buildings all across the UK, including, for instance, the new Coventry Cathedral, built with cement lime mortars, built throughout with those mortars, and those mortars with a high free lime content are offering excellent functional performance. They are not promoting decay, even in the presence of dampness. And this amplified by Rudge Memorial Chapel, also in Lincoln, built 1938 with weak cement lime mortars on analysis, and Indiana limestone. These have displayed appropriate sacrificial behavior in response to poor architectural detailing, poor weathering detailing. But of course, well, not of course, but as it happens, where those mortars behave sacrificially, they were repointed with a cement sand mortar, and that has reversed the equation, very sadly. But equally, we see similar behavior in NHL mortars. Lincoln Castle, a new eco build and repair of an old build with NHL. Salt-induced decay of Ancaster limestone in the new build 2 years after construction. No more sacrificial mortar behavior. The curtain wall of the castle, on the other hand, saturated and increasingly frost damaged, with chunks of stone having to be picked up on a daily basis in midwinter. Salts here upon brickwork pointed with NHL, but of course built with a hot mix in molten. Salts on the top right, poulticed from a salt burdened porch of Holy Trinity Church, which had already caused significant decay of the arises of the stonework. And shortly after repointing, these mortars are not white. They're showing those salts. Those salts are being poulticed from that fabric. 5 years later, those salts have disappeared, and the mortars remain sound and well bonded. Perennially wet cement pointed limestone and top left. I look at this every day out of my window. Saturated NHL pointed brickwork at low level, top right. Earth lime built barn repointed with hot mix lime mortars on the right. I don't need to say much more. Similarly dry fabric at the top of this tower in Bywell, Northumberland. Hot mixed airline repointing of a Saxon tower built with very similar proportioned mortars. Lower tower retains cement pointing. The upper tower is dry and free now of organic growth. It wasn't cleaned at the time of repointing. It has self-cleaned as the stone and the fabric has dried, preventing algae and lichens from getting a foothold, unlike on this cement pointed material below. Left and right, wet cement pointed buildings, porous stone in both cases. Bottom left, mask hall, grade 1 listed, perennially wet. This photo wasn't taken on a rainy day. On the right, a building of very similar geology of construction, but repointed with a hot mixed airline mortar. The Archibald Moffat House in Dumfries and Galloway, a very wet part of the country, clay building mortars, pointed with NHL 5 2 years before the photo top left was taken. Below right and below left, 2 weeks after repointing with a hot mixed airline mortar and after overnight rain, which had stopped only 2 hours before these photographs were taken. So what's going on here? Drawing on David's incredibly important research, David Wiggins's research, we see that typically a hot mixed lime-rich mortar, air lime or feebly hydraulic lime, has a very high density and proportion of 1 micron pores or in the vicinity of capillary active pores. Compare that on the right hand side to the pore size distribution in an NHL 3.5 mortar, and we see very few of those pores and far more pores which are ineffectively porous. And when we put that same graph alongside a graph of the pore size distribution of a SEM2 cement mortar, we see minimal difference in effective porosity between the two. So buildings, frost really gets a purchase when buildings or structures become absolutely saturated. This 18th century kitchen garden wall, the pointing has not been carried out on the copings for many years. It was pointed with a very, very hard, dense cement mortar and is perennially saturated, as you can see on the right hand side. On the left hand side, this saturation, also on the shady side of the wall, has led to extensive frost damage of the oolitic limestone, which of course has a perfectly optimal pore size distribution as well, being calcium carbonate. The frost damage to this stonework far more extensive than is apparent in these photographs, as I discovered when I had to repair it. Interestingly, of course, the original mortars were earth lime, one would say, looking at them, but on analysis were made with the very finest sharp river sand, with 9% clay actually added by the masons deliberately. The NHL research done by Cristiano Figueiredo offers more insight perhaps into what's going on with the NHL mortars. This is only after 360 days. You can see all of the NHL mortars are continuing to gain strength at this point after 1 year, whereas cement lime mortars, a 116, clearly too hard at 10 newtons, but a 129, actually not as strong as some of the NHLs even after a year. Both of these have reached their full maximum strength after 3 months and have a high free lime content. Certainly in the case of the 129, and even more certainly in the version not tested, a 1312. The Canadian conservation mix, if you like, is 1, 2.5, 8, and that does take account of the ever strengthening nature of Portland cements. Equally, the metakaolin gauged pozzolanic mixes made with lime, they too have reached their maximum strength after about 3 months. So Astier, the more transparent of all of the producers, do offer figures for different mixes at different periods of time. You can see those 7.8 MPa for an NHL 5 after 2 years, NHL 3.5 after 2 years mixed 3.5, 3.97, 125 stronger again. 116, actually they've got a weaker result there, but still too strong in most people's opinion, I would say. And a 129 coming in at 6 MPa, more or less, in that situation. The only one of these really, which one would say is of a reasonable compatible compressive strength, is the NHL 5 line putty gauged mix. However, whatever test figures you might get for an NHL, they are the test figures for that particular bag of that particular brand on that particular day. Historically, NHLs were distrusted because of their inherent variability, not only within sources, but also between sources. And we see this here on this graph. The lowest line there, of course, is the Airline control mix, which wasn't hot mixed. And we see that the weakest on test was an NHL 3.5, but also the strongest on test was an NHL 3.5. In several cases, the NHL 2s were stronger than the 3.5s or the 5s, and so on. This is a variability between brands that is intolerable unless the specific band is specified, not just the number. Of course, the other main thing being shown here, and this is after 3 years, is indeterminate ongoing strength development. And we don't know when this stops. There is no one who can tell us when this stops. A gain of half a Newton, which we're seeing steadily after about 6 months per year, will add up to a lot of gain. And of course, this equals densification and loss of effective porosity, even so far as they had that much effective porosity in the first place. A gauge mix, which I was shocked to see 20 years later, done with putty lime and NHL at Redditch, St. Stephen's, by myself, working for Nimbus at that time, has not behaved sacrificially in a salt-burdened area of this very porous and very poor quality sandstone. The stone has behaved sacrificially in the presence of salt, and the salt burden, of course, was already high in this wall. Another issue we see commonly with NHLs is shrinkage away from the stones, indicating a poor initial bond, but also indicating ongoing shrinkage potential after the mortars have become hard. This wall absolutely saturated, green with algae on the inside leaf. And equally outside, in places where there are salts in the equation, we see the degradation and disintegration of the weaker penine sandstone. Bottom right, a repointing done by ourselves with a hot mixed Airline mortar. This is 3 months after that, but that's because we only went back after 3 months to see it. As water is absolutely essential, not only for the initiation, but also for the continuation and completion of the chemical processes involved in the setting and hardening of hydraulic limes and cements, it is imperative that the moisture should not be abstracted from the mortar too soon. Hence the necessity of protecting stucco from brilliant sunshine or of repeatedly spraying it with water. Hence also the necessity of dipping bricks in water immediately before using them, and of sprinkling a dry course of bricks with water before the bed of mortar is spread upon it to receive the next course. With lime mortar, by which Sutcliffe means an Airline mortar or a feebly hydraulic lime mortar, a moderate use of water in the same way is advantageous, although lack of it has not so marked an effect as with cement and hydraulic lime. Mortar made from cement or hydraulic lime must be mixed in small quantities and used fresh. Mortar which has once set to an appreciable extent cannot be remixed without loss in ultimate strength. Now, I hope there are people listening who might be cringing at this moment, because the ongoing hydration, one would say, if one transfers the 28-day requirement for ongoing hydration of cement mortars, when people remembered what best practice was with cement mortars, that period of initial maximum strength gain with NHLs is 6 months. And it would be arguable, indeed, to say that they need that ongoing hydration for those 6 months to set properly. If they don't get it, as Vika observed way back, if the mortars dry too fast and dry rather than cure and set, in the case of NHLs particularly, they can lose up to 4/5 of their strength. One might say that's a good thing. They're not as strong as they might be, but nor are they set properly, nor are they what they should be. Another reason we see shrinkage away, apart from the lack of initial bond, which we're coming on to, the reasons for, is shrinkage potential in airline mortars versus shrinkage potential and behavior in hydraulic mortars. So shrinkage during early hardening, this type of volume change is omnidirectional. It attends hardening through cementing action. It occurs but once during the lifetime of a mortar. Its magnitude is diminished when the mortar is in contact with an absorbent unit and is greatest when in contact with solids of zero porosity. A mortar which hardens slowly is more or less plastic when most of this type of shrinkage is completed, and can therefore be closed down. This is usually on the next day or the day after that with hot mixed airline mortars. Data obtained during an extensive study at the Bureau of Standards in the USA show conclusively that this type of volume change is not damaging either to the mortar or to the bond between the mortar and the bricks. Generally speaking, one would add. This was found to be true regardless of the magnitude of the shrinkage of mortar during early hardening. Volume changes subsequent to hardening are very different. This type of volume change is characterized by expansion on wetting and shrinkage on drying. It is cyclic and frequently is rapid if the conditions for wetting and drying are favorable. It takes place in rigid mortar that has an elastic limit. High volume changes subsequent to hardening are characteristic of dense mortars of outstanding hydraulic properties. They are lowest for straight line mortars. This type of volume change is reduced as lime is substituted more and more for Portland cement. Therefore, the higher the free lime content of the binder, the less likely this kind of shrinkage after hardening, which you can do nothing about but look at it, will happen. Sorry, there is what I can say. The likelihood is that these mortars had added air entrainment or added water repellent or both, and that has robbed these mortars of capillarity. Preserving vapor permeability perhaps, but vapor permeability is not an effective mechanism for the drying out of porous fabric, certainly not fabric that is between 12 and 21 inches thick. And this little bit of research by Claire Tawney illustrates that the addition of air entrainer all but eliminates capillarity, whilst at the same time increasing redundant vapor permeability. So, to prevent excessive water penetration into a wall, one must use an adaptable mortar. This is a mortar that can be expected to adhere satisfactorily to all types of building units. Lime promotes mortar adaptability, and a mortar rich in lime, optimally just lime, is suitable for all types of units. An adaptable mortar is first of all workable. It has bonding power. It is characterized by low volume changes subsequent to hardening. It has good extensibility, produces good strength, appropriate strength, and has a rate of hardening compatible with the methods of construction. It so happens that those mortars which have the best freezing and thawing records in laboratory tests are usually associated with leaky masonry. This is why the US Bureau of Standards very quickly, on research, moved towards weak cement lime mortars for new build in the 1920s and 30s. Cement-built buildings in the US without cavity walls were leaking like sieves. The properties that enable them to endure severe freezing and thawing in the laboratory are not properties which cause them to bond completely and firmly to various types of building units. It also happens that those mortars of relatively less resistance to these tests are usually associated with dry walls oh my goodness, what is going on? They have properties which ensure good adhesion at all points throughout the wall. Excessive dampness in itself is damaging both to health and property. So durability doesn't really or shouldn't refer uh, to the ability of a mortar to survive being saturated and then instantly frozen from 6 directions, unlike any mortar in any wall. Durability refers to the ability of a structure to maintain substantially its original appearance, strength, and soundness for many years. In masonry, the two prime requisites for durability are a dimensionally stable unit and a mortar that forms a permanent and complete bond, thereby making the structure watertight. So long as the bond is complete and even throughout and is of good extent, water will not enter the fabric of that building to any significant extent. And if that mortar is porous, any moisture that is absorbed will be quickly sent away by the action of wind and by capillarity. For sound masonry, it is essential not only to have adequate, not necessarily strong, bond strength and complete extent of bond, but also to have a durable bond starting with initial hardening and continuing throughout the life of a structure, not shrinking away later. And again, the ASTMS guidance from 2007 understands this. The durability of a relatively dry masonry which resists water penetration is not a serious problem. The coupling of mortars with certain masonry units and design without exposure considerations can lead to unit or mortar durability problems. It is generally conceded that masonry walls heated on one side and with wind on the outside will stand many years before requiring maintenance. Parapets, masonry paving, retaining walls, and other masonry exposed to freezing while saturated represent extreme exposures and thus require a more durable mortar. But these are small elements of a building overall. The rest of the building requires a mortar that will get rid of receive moisture by capillary action. Mortar, when tested in a laboratory for durability, is subjected to repeated cycles of freezing and thawing. Unless a masonry assemblage is allowed to become nearly saturated, there is little danger of substantial, or I would say of any, damage due to freezing. A wall containing a straight Portland cement and sand mortar would be strong but vulnerable to cracking and rain penetration. A wall containing a straight sand lime mortar would have lower strength, particularly early strength, but greater resistance to cracking and rain penetration. So extent of bond is very important. The two key factors influencing bonding efficiency are extent of adhesion and intensity of adhesion. High lime mortars, because of their high degree of workability, stickiness, and high water retentivity or water retention, promote excellent adhesion and extent of bond, and therefore have high efficiencies. In leakage tests carried out by Palmer, less leakage with the high lime mortars was attributed to the better extent of bond, which resulted from the mortar having high water retention and better workability. The bricklayer who constructed the panels commented on the importance of workability in obtaining good bond. Workability was found to be the most important factor affecting bond because of its profound effect on workmanship. By Kampf in 1962. Capillary action is an important process for the strengthening of the cohesive and adhesive mortar strengths, but only if the mortars themselves are appropriately workable and water retentive. Otherwise, there will be loss of tenacity and ultimate performance. For new build in the context of modern building technology and relations of production, weak cement lime mortars offer predictable and positive outcomes, though lime-rich, feebly hydraulic, pozzolanic hot mixed lime mortars would be optimal and most certainly are for the conservation, repair or construction of traditional solid wall buildings, upon which cement lime mortars should not be deployed, except in exceptional circumstances and locations. Currently used 1 cement to 5 sand mortars are inferior on all fronts, and this was amply demonstrated by the US Bureau of Standards way back in the 1920s and 30s. Although effectively weak cement lime mortars, as termed by Searle in 1935, NHLs, or perhaps better described, natural cement lime mortars, are unpredictable, inherently variable in their behavior and performance, poorly water retentive, poorly workable, and highly demanding of ongoing hydration during their 6-month period of maximum strength gain to set properly at depth. If not allowed to properly set, mortars will be wanting in tenacity and bond and may lack cohesiveness within the wall. If properly hydrated and set, they will expand, contract, and shrink away in wetting and drying cycles, depending upon their extent of hydraulicity, and possess poor capillarity and progressive diminishment of effective porosity as ongoing strength gain continues. Either case will likely deliver cumulatively wet building fabric and ultimate decay. All of these properties and characteristics, whatever the circumstance or situation, need to be delivered predictably and reliably and consistently during application and throughout a structure. Pure or nearly pure lime, which is to say non-hydraulic or feebly hydraulic lime, is optimal. Departure from the optimal is determined by the necessity of any given situation or environment, and should be no more than necessary in this situation or environment, preserving free lime content as much as possible and as high as possible in the conditions. Pozzolanic addition to an airline mortar may be achieved accurately and with predictable outcomes and without loss of workability and water retentivity. Adhesion or extent of bond when moderate addition is made. Low-level addition of pozzolan such as brick or wood ash may enhance tenacity and durability without compromise of workability, capillarity, or extent of bond. For modern new build, the gauging of cement and air lime is also predictable and offers reasonable, albeit, depending upon relative cement lime proportion, progressively diminished versions of workability, water retentivity, and extent of bond. Although always less than optimal, less rapid early strength is demanded, as in the modern construction industry, for better or more likely for worse. Natural hydraulic limes do not tend to offer predictability, being inherently variable between sources and within sources, with poor workability, poor initial adhesiveness and cohesiveness, and poor extent of bond due to very poor water retentivity, especially when mixed at a modern 1:3 proportion, ignoring historic practice. NHLs were mixed at 1:1 or 1:2 historically, and a long-term ongoing strength gain and pore size densification that diminishes already low and inadequate bond and extent of bond through shrinkage of the hardened mortar in wetting and drying cycles, as well as progressively reducing already limited effective porosity. Free lime is fundamental to all essential mortar properties. So, like for like and compatible conservation work needs to employ the same materials similarly processed and used to the same or similar ends as were employed originally, most of the time. Earth lime and hot mixed air or feebly hydraulic lime mortars meet all of the above criteria and were the preferred mortars of the building crafts historically and for so long as it was that the crafts designed the mortars. Their autonomy in this regard was eroded from the later 19th century onwards, as was the understanding of what mortars were for and what the essential composition and properties of a building mortar were. And that, I would say, is that for now.